Thanks so much. Thanks for having me. My name is Brant Robertson. I'm a professor at UC Santa Cruz in Santa Cruz up the hill, another UC school. Today I'm going to talk about the first billion years of cosmic history. Let me pull this down just a little bit. So this program really is at a remarkable time. Over the last couple of years, you may have heard of the James Webb Space Telescope. Who has heard of JWST? Most of the people in the room have heard of JWST. JWST is this amazing new facility that NASA launched a couple of years ago, which really is just revolutionizing. That's not too strong a word. Our knowledge of the early universe, especially the first billion years of cosmic time. JWST is a much more sensitive telescope than Hubble Space Telescope, and it's optimized to observe galaxies in the infrared. And as I'll tell you, that enables us to find galaxies that are very far away, because the expansion history of the universe stretches out the light that those galaxies emit into the infrared where we detect it today. So you may wonder, well, why spend all this money? What's actually interesting in the first billion years of cosmic time? We think in this program that the main themes are: how and when did the first galaxies and stars form? What drove early supermassive black hole growth? And then how did intergalactic hydrogen, the gas between galaxies, become fully reionized? And all of these things happened in the first billion years of cosmic time. So that's kind of some of the focus areas of this program. Who has heard that astronomers have broken the universe? Has anyone heard that phrase in the popular medium? No one in the room has heard that. That's, it's amazing within your own field. You see something in the media, and it just keeps speaking to you over and over and over again. So there's this idea that actually some of the galaxies that we've observed already with JWST are very difficult to explain. Okay, and if you now go and you search the internet for news articles about astronomy over the last year, you'll see this come up again and again. And today I'm going to tell you why you shouldn't go for broke. You should, take that with a bit of sugar or salt, one of the two. I don't know which flavor. What is the physics of the early universe that allows for galaxies to form, and then why do we think that maybe there's some tension there with some of the earliest galaxies that we're finding? Okay, in order to get started though, I have to just remind people of a few of the kind of basic facts of the universe, just so that we have a language to talk with. Astronomers love to use very jargon-heavy stuff. I'm going to try to cut all of that out, but some of it is just irreducible, and so I'm going to do my best to remind you of what's going on in the universe. So if we think of the universe as a pie, this is often the first diagram that people draw when they talk about the universe. We can just make a pie diagram of what's in the universe, like if I could draw a circle. And most of the universe is in a form of energy density called dark energy, DE, dark energy. This is like 70% of the universe, okay? And you may have heard of Einstein's most famous blunder, that was inventing dark energy to try to counteract the contraction of the universe underneath its own, the matter self-gravity. And this is what's driving the expansion history of the universe today. We live in a dark energy dominated universe today. We're not going to talk much about this stuff in this talk. This is just for context. Everything else in the universe here, the other 30%, is matter, okay? But it's not all matter that we're very familiar with. Most of the matter in the universe, the majority of it, say 25% of the total, I'll try to draw bigger than that, is actually in what we call dark matter. I'll just say DM, okay? And this is matter that is not made of normal matter like what we're made out of. It's not made of protons, it's not made of neutrons. We call it non-baryonic dark matter, okay? Most of this matter came from fluctuations in the early universe, so I'll show you the history of the universe in just a moment. But after inflation, this very early rapid expansion of the universe that was driven by some subatomic particles, as those particles decayed, they decayed into many things, including the normal matter that we're made out of, but it also left behind, most of the matter in the universe was in this neutral, very weakly or only gravitationally interacting matter that makes up the majority of the universe's mass. The rest of the universe, this 5-ish%, is called baryonic. We call it baryonic because it's made of baryons, protons, and neutrons predominantly, and some electrons. And this is everything that we've ever experienced here on Earth. And this is really the story of how galaxies form. We need to understand all of the stars in the universe, all of the gas in the universe form in this 5% in the context of kind of the skeleton framework of the dark matter that surrounds them. Okay. And it's really the connection between how efficient we can convert these baryons, the gas in the universe, into stars in the context of how much dark matter is surrounding a galaxy. That efficiency, we call that the efficiency of galaxy formation. And you should just remember that the overall fraction of baryons, I'm going to write it up here just because it's going to come again and again, is something like 15% of by mass. So if you take all of the matter in the universe and you say what fraction of the matter in the universe is made of normal stuff, it's about 15%. So that's kind of a magic number. Okay, there is another, so please keep this in mind. There's another set of definitions I want to remind you about. Astronomers, we deal with fantastical distances. Megaparsecs are our largest unit. You don't even need to know what that is. It's like 3.26 million light years. So we tend to not think about these phenomenally large numbers, and we try to use smaller numbers to make it a little bit more palatable. And one of the most interesting numbers that we have is something called the redshift. Okay, so as the universe is expanding, light that's emitted from very distant objects gets stretched by the expansion history of the universe. So if I want to define what redshift is, I'll do that here, redshift. So if we have some light that has some wavelength, and we're thinking of some photons that are traveling from some distant star to us here in the present day, and this is an expanding universe. The expansion of the universe will take the light, the wavelength of the emitted light, and stretch it out by a factor of 1 plus the redshift z. Okay, this is the redshift. And redshift z is related to the scale of the universe as it's expanding. So if I think about the distance between 2 points in the universe at some time, we'll call this A1, and then some other time, A2, these are the same points at 2 different times. We can relate the scale factor of the universe, the physical distance between these objects, as equal to the scale factor times something we call the co-moving distance between them. And the scale factor here goes between 0 and 1, and it's 1 in the present day, it's 0 in the past. This scale factor A is just related to the redshift by 1 over 1 plus z. Okay? So when we're talking about redshift, we're actually encoding the past. When we talk about redshift larger than 0, the current redshift of the universe is 0. When we talk about redshift 10 or redshift 15, this is a long time ago in the past. And so I'm going to write some numbers just up here to keep track of. Let me do it again here. So I'm going to say that the scale factor of the universe is 1 over 1 plus z. And I'm going to tell you some important times in the universe that you might be interested in. So today, we have that redshift is 0, and the age of the universe is like 13.78-ish billion years, gigayear. Okay, this is a 13, not a B. And then you might say, well, what is the redshift corresponding to the first billion years? That is redshift, it's about redshift 5.7. And this is 1 billion years after the Big Bang. Okay? But we can go even further back in time. So you might say, when is the time that the very earliest galaxy that we know about was in existence? It turns out this is a huge deal in astronomy. It turns out that that is about redshift of 14.3 which the time is like, I hope I get this right, 280 million years? So, I can't remember. I got some nods. Okay, so very quickly between the time of the first galaxy that we've been able to find with JWST, before JWST, the earliest galaxies we found were maybe 900 million years after the Big Bang. So we've really stretched with JWST well past what HST could see, all the way out to a time of Redshift 14.3, which is about 280 million years after the Big Bang. Okay. Now, let me try to give you a diagrammatical view of the history of the universe to give you some context, and then we'll start talking about what we know about galaxy formation, okay?
This number is it that the number of galaxies seems to be getting small to that scale, or that you just can't see it?
That's the most distant galaxy we know about. Now, whether the galaxies are dropping in abundance is something that's actually a very interesting question. It seems as though they're slowly going down in abundance, but not as fast as you might have expected from before JWST. And that's actually a big story that we want to talk about. So this is the most distant thing that we know about. Okay, and really there's only a very small handful of galaxies above a redshift of 10 that have been confirmed in terms of their distance. So in the first 500 something million years after the Big Bang. Okay, they're very, very faint, they're very, very far away, they're very hard to actually confirm their distances by looking for spectroscopic evidence of how far away they are. I can explain that a little bit later. Any other questions before, yes?
How do we estimate 15% value?
Yeah, so that's a very good question. There's multiple different ways that's done. You can look at the statistical information in what's called the cosmic microwave background, which I'll explain in just a moment. And that actually gives us information about the relative amount of baryonic material versus non-baryonic material. And that's consistent with this 15% of the matter being in baryons. The fraction of the energy density in the universe, matter and energy have some equivalence, is about 5%. Okay. All right, let me erase this, and then I'm going to draw you kind of the history of the universe in one diagram. Okay. So just give me a moment to erase. So, we call this program the first billion years. Of course, time t equals 0, or whatever that means, is the Big Bang. And I'm going to completely ignore what happens in the Big Bang for the safety of people in the room. So, all that you need to know is that very, very early on, something like 10 to the minus 23 seconds after the Big Bang, the universe was expanding extremely fast under the influence of subatomic particles, called scalar particles probably, that allowed for a very rapid, much faster than the speed of light, expansion of the universe. Those particles annihilated, so they self-annihilated, they decayed into all of the other matter that we see in the universe. And then there was a point of nucleosynthesis that happened in the first few minutes after the Big Bang, after which the universe was almost entirely made out of the matter in the universe, hydrogen, helium, and dark matter, which we don't actually know what it is, okay? So after that point, the universe continued to expand, and I'm going to draw all the way here to give myself a lot of room. And I'm sorry I can't draw a straight line, but that is what it is. Okay. So you can think of this as the expansion of the universe, and today we're going to be over here at the middle of the blackboard at z equals 0 time t equals 13.78-ish gigayear. So after the inflationary epoch, the universe was very hot and dense. So I'm just going to draw hot and dense. But it expanded and cooled over time to the point where at this period in time, when it's very hot and dense, all of the hydrogen in the gas, or in the universe, was completely ionized into protons, electrons. There are also helium nuclei floating around, and subatomic particles, dark matter, that don't interact with light or electromagnetism. And then it expanded and cooled to the point where electrons could recombine onto protons to form neutral hydrogen. So that epoch here, we call this the cosmic background, can't spell, radiation epoch. Today we observe the remnants of this cosmic background in the microwave, so that's why we call it the cosmic microwave background. And what's important to note is that before this period, the opacity of the universe, kind of the fogginess of the universe, was extremely high because all of the photons, and I'll write photons as a gamma in this talk, all of the photons in the universe could scatter off of the free electrons through electron scattering, Thomson scattering. Okay, every electron can interact with a photon and scatter it. And so they remained tightly coupled, and the photons wouldn't travel very far before they ran into another free electron, and so they would just bounce around. But after this point, once all of the free electrons in the universe recombines to form neutral hydrogen, which we'll write with a capital H, those photons could travel more or less freely throughout the universe to today. Okay. And after this point, we had a lot of neutral gas in the universe. Hydrogen and helium were mostly neutral after that point. But there really wasn't much going on. Okay, I'll draw neutral gas like this. There wasn't much going on. Structures have not really formed in earnest after recombination. The typical size scale of density perturbations in the universe was something like 10 to the minus 5 at the time of recombination. And so we had to wait for those density perturbations to grow to large overdensities in the universe that could allow for gas to form inside of the dark matter potential wells in these density perturbations. And that's eventually what led to galaxies. And I'll talk about the details of that a little bit later in the talk. Okay, so at some point, we know that there were the first stars that formed in the universe. And what I'm doing is I'm showing the stars, and then these bubbles around them are ionized gas bubbles. Okay, so the first stars formed, I'll talk about that process soon. The first stars probably formed at a redshift of about 30, which conveniently is 100 million years after the Big Bang. Okay, so that's about the time when the first stars could actually form within the dark matter structures that were developing early in the universe. And of course, if you have multiple stars, then you might call that a galaxy. And so we think the first large galaxy started forming sometime between redshift 30 and hopefully by redshift 14 when we see the first ones observationally. Okay, and the number of these galaxies grew in both luminosity and in abundance, such that the bubbles that they carve out in the universe could grow in size. And eventually, those bubbles could grow to the point where they could start to overlap. And then at that point, if you think about why are these stars ionizing the gas, they're very hot, these stars that are first forming. They're massive and they're very hot, so they produce ionizing radiation, hydrogen ionizing radiation. The mean free path of those ionizing photons increases dramatically as these bubbles begin to overlap. And then eventually, we find that these bubbles completely dominate, and the whole universe eventually, sorry, I should just not draw that side, the whole universe eventually, all of the gas in the universe becomes ionized. Okay, and we think that this reionization epoch occurred in the first billion years of cosmic history. And it's the last major phase change in the universe in cosmic time. It also happens with helium at lower redshift, but fine, we'll just say it was the last major phase change of the universe at large scales. Okay, it happened in the first.
What fraction of the matter is invariant?
So the fraction of the matter.
Sorry, what fraction is in galaxies?
What fraction is in galaxies? A relatively small amount. Yes.
Most of it is ionized gas.
Most of it is ionized gas. Yeah, outside of galaxies. Yeah, that's correct. Okay, and then the number of galaxies actually increases until a time which is about redshift, say, 2 to 3. So there are more and more galaxies that form over time per unit volume corrected for the expansion history of the universe. but then actually the rate at which galaxies are forming declines to the present day. Okay, and so this, we're just going to ignore everything that happened in the last 10 billion years of cosmic history. That's fine. Today, actually, 12.5 billion years. Today, we're just going to talk about the first billion years. Okay, so diagrammatically, this is kind of a brief history of the observable universe. Does anyone have any questions before I go on to talk about physics? Yeah.
Describe the reionization again. If the galaxies have very little mass, how are they figuring this reionization?
It's because they produce a large number of ionizing photons per unit of mass converted into stars. So I'll actually say more about that process a little bit later. Any other questions? Yeah.
Black matter, does matter as this galaxy, whatever, in some way, when you're counting galaxies?
I'm sorry?
Black matter is a part of it?
Yes, and actually it's an important part of it because we have to understand the mapping between galaxies and dark matter, and that brings me exactly to the next thing I'm going to talk about. So just hold on with it's a great question. Just hold on. Anything else? Yes?
Can you go over how you measure the redshift? I understand if you
Ah.
use the physical distance, it would be easy to calculate, but we don't know that. Could you use time?
So what we do is we use features in the spectrum, hydrogen lines, for instance. So, the bluest hydrogen line is Lyman alpha. And so it's very distinctive when you measure Lyman alpha because it can be a strong line, and then blueward of Lyman alpha, all of the intergalactic hydrogen between us and the object absorbs the light. So actually we know what the emitted frequency of the line is. We can identify it's uniquely Lyman alpha, or we can maybe identify that it's hydrogen Balmer alpha. These are just series of hydrogen lines. And then we observe them at a different wavelength in the infrared, and then you just divide the two, and that gives you 1 plus Z. Yeah.
Yes, so this might be a very dumb question, but is it obvious that if you look at these things that are so far away and have gone through so much history, that the amount of redshift the photons on is always the same, whether where you're looking in the universe, or could it be paths that lead to much more redshift than
Okay, so at any one time, if they were just static in the flow of the universe, they would have exactly the same redshift. But what happens is because under the forces of gravity, there's some neighboring object. It might be tugged a little bit one way or the other. And then you get a Doppler shift from the peculiar motions of that galaxy relative to kind of the background expanding frame. And then that can change the redshift a little bit. And so they won't all have exactly the same redshift at the same distance. Things that are very far away have much, much larger redshifts. In fact, I should have mentioned that recombination, when the cosmic microwave background was emitted, that is redshift of 1100 approximately, to give you some context. So that's about the most distant thing that we can observe at all is the CMB. Beyond that, we can't really observe except for with gravitational radiation or something. So this is kind of the limit on the highest redshift that we see. And then, only observations out to about here, everything this way until we get to the CMB we haven't observed. Okay, let me go on just in the sake of time because I'm already deep within my time here. And I'm going to go on to the kind of the first topic. So now that we've laid the context, when did the first stars and galaxies form? I'm going to talk a little bit about why it's interesting to study the development of those galaxies over cosmic time in the first billion years. I'll need to erase the board though. So let me give myself a little bit of room. And let me just get my notes so I don't miss anything. Okay, I'm going to talk, just show you, give you a context of what's happening in the present day. Okay, when we talk about understanding the connection between galaxies and dark matter halos, there are kind of some simple ways to understand that today, at least. Okay, so so let me just give you some context. This is the present here, and I'm going to draw a diagram of the abundance of galaxies. Okay, so on this axis, I'm going to take the log of the number of galaxies per unit luminosity. Okay. We'll call this the luminosity function because we're just counting up the number of galaxies per unit luminosity. And then here I have the log of luminosity, and it's increasing this way. And astronomers love to be, idiosyncratic, and we like to plot things in reverse and stuff. I'm going to plot it in the most natural way with luminosity increasing to the right. And so what I'll do is I'll just go in the universe, I'll count up the number of galaxies per unit volume in the universe, and it looks something like this. At low luminosities, so luminosity is increasing this way. At low luminosities, it's somewhat of a power law. There is a knee and then an exponential cutoff in that distribution. Okay, so we know that there are faint galaxies, so this is the power law. So the number of faint galaxies increases as a power law to small luminosities. There's an exponential cutoff at bright magnitudes. Okay, so that tells you how galaxies are distributed volumetrically as a function of how bright they are. But then the question was, well, if galaxies form in dark matter halos, how does that compare to the distribution of dark matter halos in the universe? There has to be some connection between galaxies in those dark matter halos. And so now if I change this to be the number per unit mass, and I change this to be log mass, the distribution of dark matter halos in the local universe, we get this from simulations, looks something like this. Okay, so there is, yes, Peter. Yeah, so that's a question I'm going to avoid until the end. That's an astronomer question. But basically, a dark matter halo is the distribution of dark matter around, around a galaxy. Every galaxy is embedded within a spherical distribution of this dark matter that we've been talking about. The baryonic component of the galaxy is on much smaller scales than the dark matter halo. The dark matter halo may be more than 1 million light years across, but the size of the Milky Way is like 100,000 light years across.
Most of the dark matter in those halos?
Of some size, it all is, roughly, okay, almost all of it. But some of those dark matter halos can be very small. I don't want to get into too much detail, but in galaxy-sized halos, that isn't the case. Okay, so there is a difference between the number of dark matter halos. Peter was trying to bail me out a little bit, just so I could define what a halo is. Okay, these are the regions within the dark matter distribution where galaxies are formed. I don't have a simulation to show you, it's very evocative, but you'll have to use your imagination. These are little spherical distributions, spheroidal distributions, within which there might be a galaxy. This is the halo of dark matter, and this is the galaxy. Okay, if I could spell. All right, so now a lot of galaxy formation is understanding the difference between these two. There is an offset in the abundance of these dark matter halos compared to the abundance of galaxies. Now, some of that comes from the fact that we're looking at the mass of dark matter here, and we're looking at the light of galaxies there. Okay, so you can think about a mapping between, I'll just write mapping, between dark matter halos and galaxies. And that in itself is some kind of efficiency. Okay, we think about that as some fraction of the total amount of baryonic normal material within a dark matter halo can form a galaxy. And you can see that that efficiency is not necessarily large. It isn't large in the present day. So this mapping, you could say, well, if I take the amount of dark matter in the universe, so let me just say, what is the typical mass of a galaxy? Well, you might think the mass, of a galaxy might be this baryon fraction times the mass of its dark matter halo. That is definitely not the case in the present universe. It is lower than this. There's some efficiency, which I will call eta. And eta here is less than 1. And actually, sorry, I keep tripping on that. For the Milky Way, just to give you some sense, the mass of the Milky Way, the stars in the Milky Way is, 3 times 10 to the 10 times the sun, whereas the mass of the dark matter halo of the Milky Way is 1 trillion solar masses. Sun. Okay. So if the efficiency of a galaxy formation was 1, this would not be 3 times 10 to the 10. It would be 15 times 10 to the 10. So the efficiency of galaxy formation for the Milky Way is something like 20-ish%. And it turns out that the Milky Way is here. Okay. And you can see that that is the point that is closest to the dark matter halo distribution. So actually, galaxy formation is the most efficient at about the Milky Way scale. It's less efficient at higher masses and less efficient at lower masses. Now, a lot of the work of people in this room and the community have shown in the present day that this discrepancy here probably owes to what we call stellar feedback. That's supernova explosions and radiation from stars reduce the efficiency, the conversion of all of the available gas in the halo into galaxies. It reduces that. And then on this end, it's actually some combination of supermassive black holes. They have some gas accreting onto them. They heat up the surrounding material and prevent it from further accretion. And then there's also some cooling efficiency in that very, very large dark matter halos have less efficient cooling. Okay, so some combination of the two effects.
One thing you're writing is the mass of the normal.
Yeah.
Then you're also doing the luminosity.
Yes.
And which things are cooling and so on. I guess I'm a bit confused by.
Yeah, no, that's completely fair, and that's actually what does efficiency mean? So we observe luminosity. We can, in some cases, measure stellar masses. In the local universe, if I had done stellar mass, it would look very similar. In the distant universe, it's very difficult to measure stellar mass, so we're kind of stuck with luminosity. That's why I was starting with it. But indeed, if you have a stellar mass of a galaxy that's some fraction of its dark matter mass, then you could say, well, how bright are the stars? And that would tell you how to map, if I take dn, dm, dark matter, we know that that's something like dm dark matter, dm baryon, other way, baryon, dm, dn, dm baryon. And you could do the same thing with luminosity. Okay, so this is the mapping between the number density of dark matter halos and the number density of galaxies. There's some conversion, which when we talk about stars, we call the stellar mass to halo mass ratio. Okay. So the key points to take away are that this fraction is very small for galaxies in the present day, and that's right, it's small for galaxies in the present day. Okay, so now what I want to do is I want to kind of take us and talk about the history of the universe from this point. Yes, please go ahead.
So is the notion that the matter in the halos gets converted into baryonic matter, or is it that the matter in the halos aggregates?
Yeah. Yeah. So I should have said this. So there's not really a transfer between dark matter and regular matter in the universe. This fraction is pretty much set at very early times. So the dark matter just provides kind of the skeleton within which the galaxy forms. You're not converting dark matter, non-baryonic material, into baryonic material. That's not what's happening. What's happening is the gas somehow cools out and then forms stars. And the process by which, some fraction of the gas that's available to form that galaxy actually does, that efficiency is much less than 1 in the present universe. And that's kind of what we're trying to get out. Okay. So let me just give you a description, and I can see we're definitely running short on time, so I'm probably going to cut out half of the talk, but that's okay. That's the way it goes. All right. So let me talk about now rewinding. So this is in the present day. What is happening at higher redshifts? Okay, if I kind of show you the same plot of the number density of dark matter halos or the luminosity function of galaxies, how is that different at high redshift? Now, for dark matter halos, so let me draw dark matter halos here. The time evolution, if I take log mass, and this is dn d log m. I showed you at the present day, it looks something like this. Okay, this is a log-log scale. As time evolves, it actually starts doing something like this. It bends, and then it kind of falls down. And what's really important here is that the number density of dark matter halos as a function of how some mass ratio is falling dramatically. Okay, so if I take a dark matter halo of, say, 10 to the 9 solar masses, and I compare it with a dark matter halo of something like 10 to the 10 solar masses, in the very early universe at redshift of 12 or something, there are hundreds more of these galaxies than there are of these galaxies.
So time is going this way.
This is time going this way. Backward. So, sorry. Yes, that's correct. Time is backward. Negative, positive, yeah. Yeah, yes.
Based on basically assuming dark matter is something that only gravitationally interacts.
No, I mean, so first order, yes. Now, we don't think that dark matter necessarily is gravitationally only interacting. It might be interacting at the weak scale, the weak force scale. If it's not, then actually it'll be really, really hard to find dark matter anytime soon. So let's hope that it actually interacts weakly. But it does not interact through the strong force. Certainly does not interact through the electromagnetic force. Okay. Yes. General relativity. You had me at simulate, but general relativity often on these scales you can ignore. To first order, you have to worry about the expansion of the universe, but the detail of gravitational attraction, we're not in the strong regime unless we start talking about black holes, and then, yeah.
This novel law and this sort of more exponential physics must come out of some sort of
That-
model that says inhomogeneity.
Okay, yes, that's correct. So the background, talking about the number density of dark matter halos and actually how galaxies form, we do simulate that from first principles being limited by spatial resolution primarily. So we have to make some artifices on small scales to recover from the fact that we don't, track every single physical process from first principles. But we do model the gas radiation and cooling. We do model how it becomes overdense and the rate at which it forms stars, and then the impact those stars have on the surrounding gas. So we do go through all those things, and I would show you that, but on a Blackboard talk, it's difficult to do. So it is definitely the case that you'll have to trust us when we talk about dark matter halos, which don't involve any of that physics, just gravitational physics, that this is a fairly robust prediction of what the simulations say. And the important thing to get across is that in the early universe, the number density of dark matter halos is dropping dramatically as a function of how massive they are. Okay, and if you change by a factor of 10 in mass, then the factor of the difference in abundance is like more than a factor of 100. It's like the factor of 300. Okay. Now, why is that important? Well, I told you, you might say, okay, well, that's fine, galaxy formation's not efficient. We heard that in the present day. If I just take this and I apply it to what we're learning, a simulation of the universe, dark matter halos in the early universe, I would expect that, well, the dark matter halos would, also have an efficient galaxy formation, and the number density of galaxies in the early universe should drop dramatically. Okay, so if I go far enough back in time, the number density, the abundance of galaxies should drop dramatically. And actually, if you go back, if you rewind, maybe about 10 years or so, something like that, and you just simply count up the rate at which, and this is the cosmic density of star formation. So this is how fast stars are forming per unit volume in the universe. And then I plot that as a function of redshift. So time is increasing this way for those of us. This is, say, redshift 0. This is redshift 2 to 3. This is redshift 8-ish. And this is the log. Okay. We found that it was increasing as we went back in time. There were more stars being formed per unit volume out to the last 10 or 12 billion years. But then it fell down And then with HST, this is what we had discovered. There were observations of galaxies throughout this entire period of time. But HST kind of ran out of juice around redshift 8. It just wasn't big enough. It didn't have enough infrared sensitivity. And there was a lot of discrepancy between the results that people had inferred about galaxy formation. And kind of around 5 or 6 years ago, the consensus, I think, in the community largely was that the number density of star formation in the universe would drop like a rock above a redshift of 8. I didn't personally buy into this, but lots of other people did, and I wrote a review article just taking the view of the community, but that's fine. So this number density of galaxies, you might say, why should that happen? Well, it's because of this. If galaxy formation is inefficient and it has roughly the same inefficiency as it does today, then the number density of dark matter halos dropping like a rock means that the number density of stars being formed in the universe should also drop like a rock. Okay, but that's not what we've discovered with JWST. If you go with JWST and you measure this quantity now, with JWST it looks something like this. So JWST has been able to find lots of very high redshift galaxies, more than many people were anticipating. Okay, and there are so many of them that if you take these simple arguments of how efficient star formation should be, and you just apply them to the dark matter halo distribution that we know is out there from cosmological simulations that predict many other things that have been confirmed, then this is a lot of tension. And in fact, there are people who have claimed that it is so difficult to do, to form some of these bright galaxies in the early universe. It's so hard that actually cosmology is broken. That's what they mean. Because we're finding galaxies that are so massive in stars, at least that's what we infer from them, that they cannot be easily explained within the cosmological model that we usually adopt. Okay. Now, as people in the room have already highlighted, and you've asked some very important questions, how is this possibly wrong? Well, trust me, if it seems like it's wrong, it probably is wrong. That's been the story of galaxy formation for a long time. And, really the question is how efficient the star formation is. Well, maybe it's a little bit more efficient than it was in the past, or a lot more efficient. But also we can make observational errors. Okay, we can observe some amount of stellar mass, which takes a model to interpret what you see in light and determine the amount of stars that corresponds to. Those models may be incorrect. Okay, or maybe there's some issue with supermassive black holes. So supermassive black holes can actually contribute light to a galaxy because the accretion onto the black hole actually produces light, and this can resemble the light that is produced by stars. So you might actually get the mass of the galaxy entirely wrong because there's a supermassive black hole at the center. Now, you have to explain how the supermassive black hole got there. It pushes the problem to a different point, but actually it's a problem that many of us are much more comfortable with than some of these other issues with the formation of early galaxies. So now, so I don't know, how much time do I have left? 5 minutes. Before questions or? Yes, okay. So let me just, let me tie this to some of the other topics. So, I barely got through this first topic. There are these two other topics. So let me just talk about, in words, how these other topics connect, with apologies to the people in the room who are the experts in those areas. Okay, so I mentioned that there are a large number of galaxies in the early universe, some of which appear to be overly luminous or overly massive. And I also told you that there may be supermassive black holes that exist inside of those galaxies. And I was going to go through a whole lecture on this, but basically without going into too much detail, if you think about the way that supermassive black holes grow, they go through the accretion of material. And that material often becomes very hot because it's compressed by or heated by the gravitational potential well supplied by the black hole. And so it's highly ionized. And so as the material infalls, it'll actually release gravitational potential energy as radiation, but that radiation encounters ionized gas. And as I told you, in the early universe, ionized gas is very opaque to radiation. And so there's actually a balance that kind of limits the amount of material that a black hole can grow every so often. Actually, it's called the Eddington limit. And it means that black holes can only grow by an E-folding every 45 million years or so. Okay, and if you think about growing a supermassive black hole that might be big enough to masquerade as a whole galaxy, those are black holes that are maybe 1 million solar masses at redshift 10 in the first 500 million years of cosmic time. But then how did you grow 1 million solar mass black hole in only 500 million years if an E-folding is 45 million years? That means that you would have had to start growing a black hole that's only 1,000th of that size, something like at redshift, I don't know, 30 or so. Okay, but we think, you might say, well, you know, what seeds the black holes at redshift 30? I told you in our diagram that that's actually when the first stars form. But the first stars, the people in the room will tell you, the distribution of masses of the first stars that are growing at redshift 30 are not usually 1,000 solar masses. They usually form black hole remnants that are much less than that. So there's some kind of discrepancy between the available population of the early black holes that are there that can then grow to form these luminous black holes that we're seeing at high redshift, and the population of seeds laid down by the first stars that are forming in the early universe. And so maybe the black holes grow more efficiently than you would expect from this argument of the limitations of electron scattering that I mentioned, the Eddington limit. Or maybe there's other ways of growing even more massive star black hole seeds in the early universe, like the effects of the first star on the second star could potentially have an impact that would allow for even more massive stars to form early on and form large black holes. So there's just too much to discuss. I'm sorry that I didn't get it all in. But definitely come to our talks and talk with us while we're here. We'd love to have more conversations with you, and I hope you found this somewhat enjoyable. Thank you for your time.
More questions?
Probably another dumb question. Why is it obvious that the dark matter doesn't form seeds for black holes?
Why is it obvious that the dark matter doesn't form seeds of black holes? Well, you know, the distribution of matter on large scales is relatively diffuse. Okay, it's overdense by a factor of maybe 200 relative to kind of the mean density of the universe. That's how overdense you have to be to form a galaxy, let's say. But the dark matter doesn't have any mechanism really to dissipate its energy. It can't cool effectively because it would have to radiate. And it doesn't interact with electromagnetism. So the dissipative process of forming galaxies is really a story of the baryons dissipating. The dark matter can become overdense through self-gravity, and actually there are ways of getting the energy transport of dark matter so it can lose energy angular momentum to other parts of the dark matter and fluff up the outside and contract the inside. But you can't form a black hole easily from the dark matter itself. Now, there may be early black holes that are formed through subatomic physics processes, but I'm not going to go into detail. Those would be very early on. Yeah. Oh, well, so initially they're distributed basically the same. Now, in the very early universe, they do feel somewhat different physics. And the reason is there are a lot of photons around, and so the baryons couple to the photons in a way that the dark matter doesn't directly. So there's something called baryon acoustic oscillations, which are basically pressure waves in the early universe. And we see evidence for those both in the cosmic microwave background, but also in the distribution of galaxies today. It leaves a fingerprint on the distribution of galaxies on like 150, sorry, let me do it in light years, like 500 million light year scales in the universe. Okay, and so they are initially distributed more or less the same, but then the dissipation of the baryons, they start distributed with the dark matter, they can cool out, and that allows for them to contract. Of course, when they contract, there will be angular momentum, and that angular momentum will cause them to spin up. And that's kind of like the hand-wavy, not quite right, 25-year-old view of the way a disk galaxy might form. Yeah. Yes?
I wonder about this, you mentioned the tension. So when people are saying that, we are seeing galaxy too early as compared with what was kind of what is your comment on this? Because how serious is all of this?
Yeah, so like I said, you know, there are lots of ways out of that particular issue. So either you know, if really what you're doing is you're comparing the number of galaxies you see with the number of dark matter halos that are out there, okay? You say that things that have comparable abundance are the same thing. And then you compare the dark matter halo mass with the baryonic mass that you infer from the observations. Okay, and those things seem to suggest for some galaxies that there are too many baryons in the galaxy compared even to this number, which would require an efficiency greater than 1 of the conversion of baryons into stars. But those are, like I said, there are ways out of it. One is that supermassive black holes can masquerade as some of the stars. That'll reduce the amount of stars you would need. Also, our models for interpreting the amount of stars given what you see in light are wrong, largely. It takes a lot of sophistication to do that correctly. So that probably also reduces the importance. But then there can be questions of how much dust there is in the galaxies. There are a variety of other things that could get you out of that problem. And really that's what this program is about in a large way, is like understanding what is physically true about those galaxies, and then observationally how you're mapping what you see to what we trust in terms of the theoretical models for the way that galaxies form. Does that answer your question?
Yeah. So what we will probably take for you less than 1 billion years.
Well, you know, yeah.
That was basically my question with the agenda of like, do you have a favorite resolution? Or like,
Do I have a favorite resolution? No, I don't want to go on the record. I mean, so, you know, my view is that it makes some sense to me that galaxy formation would increase its efficiency at early times because the dynamical timescales are extremely short. Okay, and so things happen very quickly, and so it's difficult if you try to regulate a process. The regulation of that process might occur on 10 million year timescales where you have stars that form that then explode as supernova and they surround, you know, they heat the surrounding gas. That happens on the timescale of the stellar lifetime, which for massive stars may be 10 million years. But the dynamical timescale at the center of these early galaxies are comparable to that. So, you know, you have to actually arrange that all of the stars are doing something kind of in concert at roughly the same time to really prevent star formation from occurring in those galaxies, or regulate it in a very intense way. But I think there are many other things. I think the supermassive black hole angle is very, very interesting and important. But then I think as people will know, I've been doing a lot of data analysis over the last couple of years. And so I am aware of kind of that disconnect between the observations and the theory. And I think that's important to try to you know, close that gap a little bit more than we have in the past. All right, thank you so much for your time. I really appreciate it. Thank you.